Good morning. Are there any questions on anything before we get started? Did you guys get the email I sent with the syllabus for the labs?
Yes.
Okay. All right, so I think we'll do 9 labs. I think most all of them are posted on the YouTube channel. Maybe the last 2 aren't posted, but I'll get those. That'll be a while. And so tomorrow I will send you a worksheet. I'll send you a data sheet and a worksheet to do for the first lab. The first lab is composition of concurrent forces. And it's basically adding vectors. So there's an intro about vectors and so forth that you need to watch and fill out the data sheet, send it back to me. We'll make it due like Monday or something. I mean, I think I put on the syllabus 2 days for the worksheet, but okay, Monday, whatever, so, okay. Any other questions about the stuff we did last time?
It's not a question about the stuff we did last time, but it's about the lab syllabus. It says we have to do a
Says you have to do a what? I can't hear you for some reason. Oh, Lord. Are you guys there?
You cut out like talking just now.
Yeah, something happened. I don't know what. Hold on a second. Okay. Am I back?
Yes.
Okay.
You can see the board.
Okay. All right. I don't know. Okay, so what was the question?
In the syllabus, it said something about like a written lab report. Is that
Yeah.
what we're also going to have to do, or is it?
Yeah, the 3 lab reports that are underlined in the syllabus, those are written reports. So there's a template for those, and I'll fix up that template to fit what we're going to do over the summer. And you'll have a week to turn that in. So they're really straightforward, I think. I don't think you'll have any trouble with that. When we get to the one where you have to write a report, which is acceleration due to gravity, that's the first one. Yes, good question.
You'll let us know when we have to do one.
Absolutely. Yep.
Okay. Thank you.
Sure. Any other questions? All right. So last time we were talking about motion in one dimension as opposed to multi-dimensions. And we had a couple of, or 2 or 3 things. We talked about, ooh, that's not very good. Let's see how this looks. That's even worse, okay. Well, guess I'll go with black. Okay, we had the displacement. Displacement is a distance, and it's not only a distance, it's a distance in a particular direction. So if we write down, the displacement is delta x, which is equal to x final minus x initial, okay? And if delta x is positive, that's a displacement to the right. If this is the x-axis, here's 0. If you started here, and you end up here, that is a positive displacement. If you started here and you end up here, okay, that is a negative displacement. You would have a negative value for delta x. All right? It's always x final minus x initial. So displacement's not only how far you went, but in what direction. Then we had the velocity based on this displacement. So velocity, and we'll say average velocity, is equal to delta x divided by delta t, where delta t is the time it took to cover this or create this displacement delta x. So I can write this out from what I just wrote down earlier, delta t, it's x final minus x initial divided by delta t. Now, this also has a positive and negative. If you have a positive in front of v average, you are going in the plus x direction. If you have a negative, you're going in the negative x direction. Okay? So this was velocity. There's a difference between velocity and speed. Speed is simply the ground you covered and divide it by the time for that ground. Okay? It's just the distance you traveled, not the displacement, but just your total distance on your trip divided by the time it took. Okay? This is different. Then we had acceleration. Acceleration is the rate of change of velocity. It's how quickly the velocity changes. So acceleration, and I'm not going to put the average down here. Acceleration for us is average is instantaneous and so forth. So this is delta v divided by delta t, and certainly acceleration could be positive or negative depending on the direction of the acceleration. And this is v final minus v initial divided by delta t. So that's what we had last time. We did that example with a car or a cart taking a trip kind of thing. So today we're going to develop these ideas a little further and find some equations of motion for objects moving in one dimension. And when I say equations of motion, I mean just like we always do. Maybe you know the acceleration and you know the velocity and you want to find the time. You know the displacement, you know the time, and you want to find the velocity. All those kinds of things, okay? So I'll write these equations down. They're in the text, and once you start, by the way, on my webpage, if you look on, I don't know if I sent you a link for my webpage, but it's very easy to find. It's just like everyone else's at CBU. If you look on the webpage, there's an equation sheet for the test. That's something that I let students bring into class for the test. And it's got all these equations on there, and it is very useful. So when you're doing the homework problems and all that kind of stuff, it's nice to have that equation sheet. And all these equations that I'm going to write down are on that sheet. So we started with this, which I just erased. This V average is equal to x final minus x initial divided by delta t. Okay? We can change that around. I started to do this yesterday when everything went kaput. So we can change this around and write it as x final minus x initial is equal to V average times delta t. Okay? Moving this to the other side, we get x final is equal to v average times delta t plus x initial. So what this says is, if you know your initial position, you know the time that you traveled and the velocity at which you traveled, you can find the final position. And don't forget those SIGNs. Don't forget the signs for velocity. If your velocity was in the negative direction and your initial position was in the positive direction, you may get a negative x final, okay? That's fine, all right? So for constant acceleration problems, let me just rewrite this in one other way. This is equal to v average. Usually you'll see it written like this. Okay, we will start our times from 0, so it'll be vt plus x initial. Okay, so the average velocity times the time plus your initial position. Okay, this is a straightforward rate times time. Okay, velocity multiplied by time equals distance. All right. So for constant acceleration, if you have, which everything we do will be constant acceleration, we know that acceleration, which I just erased, is v final minus v initial divided by delta t. Okay, that's the acceleration. At constant acceleration, okay, for constant acceleration, you can move this around and you get v is equal to v initial. Let me put v final here. V final is equal to v initial plus a t. Okay? This says that if you have an initial velocity and an acceleration times the time, you can find your final velocity. Okay? Now, once again, if that acceleration's negative and this is positive, or this is negative and this is positive, okay, you have to keep track of that. Time is always positive. That's why we typically just write t, okay? It's a positive number, all right? So this is the constant acceleration velocity equation. Also, and I'm not going to prove this, but maybe it's obvious, maybe it's not. When you have constant acceleration, the average velocity is equal to v final plus v initial divided by 2. If you have a constant acceleration problem or situation, and you want to know the average velocity, you can find it from just adding the final velocity and the initial velocity and dividing by 2. Okay, just like you would average any two numbers. All right, so using this from the other equation that we had, you get x final is equal to x initial plus the average velocity, v final plus v initial divided by 2 times t. Okay, remember this is v average. I'm just substituting this in here from what we had previously. Just that velocity times time is equal to distance. Okay? So you can multiply this out and you get, let's see, what do you get? You get this is equal to x initial. The notation I have in my notes is a little different than I'm writing up here. That's why I have to keep pausing, okay? X initial plus v initial t over 2 plus V final plus V final T over 2, okay? And we also know that V final is equal to V initial plus AT, okay? So I can use that in place of V final here. So let me do that. I don't need that. Okay, so I'm going to substitute this into here. So I'm going up here. So I get this is equal to X initial plus V initial T over 2 plus V initial plus AT divided by 2, okay? And that is equal to, and all of this multiplied by t. I have a t here, okay? So I'll collect terms and you get x initial plus v initial t plus v, I'm sorry, not v, plus a over 2 t squared, okay? This equation, this is x final. This equation relates velocity, time, and initial position and acceleration to your final position. So this is quadratic. You may have to solve a quadratic to calculate your final position. Maybe you know the final position, the initial position, the initial velocity, the time, and you want to calculate the acceleration, okay? Depends on the way the problem's set up. So this is an equation that you'll use over and over and over. All these you'll use over and over and over again, but this one is important, okay? We have one more equation. I'm not going to go through all the math on, or it's really just algebra. I'm not going to go through all the algebra on the next equation. What you can do is you can make a substitution for the time in this equation and get rid of time and put this in terms of velocity, displacement, and acceleration. If you'd like to see that derivation, it's probably in the book or somewhere. Well, it's all over the place, but it's V final squared minus V initial squared is equal to 2A X final minus X initial. That's initial. Okay? Now, this is just simply the displacement. This is delta X. Okay? So we have this. I'll put a box around this. We have this equation. These are all on the equation sheet. Okay? For constant acceleration problems, which is all we're going to be doing, you also have that V final is equal to V initial plus AT. That one is on the equation sheet. And you have that X final is equal to X initial plus V average. Let me write it like this. V average T. Okay. What else do we need? I think that's it. Well, also remember that V average is equal to V average is equal to V final plus V initial divided by 2. Okay. All right. So we're going to see how to use these equations. If I had more board space, I don't. But if I had more board space, I would be able to put these equations up there and point to the one we're going to use and all that kind of thing. So you'll just have to refer to your notes or put the equation sheet in front of you and look at that. Okay. Are there any questions on this, on these equations of motion?
So for the average velocity, could it also be the like the final displacement minus the initial displacement over time?
The final displacement plus, so you want something like, I'm not sure what you mean by final displacement.
I mean, it was like delta x over delta t.
Oh yeah, sure. That's the average velocity, absolutely.
Okay.
Yeah, but sometimes in some problems you may be given the initial velocity, the final velocity, and you need to calculate the average for that. In certain situations, this is a...
It's a plug and shot, right?
What's that now?
It's just like a plugging in stuff, like what you have based off the equation.
Yeah, these are the tools we're going to use. We're going to spend some time hopefully thinking about the physics and what's actually going on. But in this 1D motion, it's pretty straightforward. It's just to get you going and get you familiar with looking at negative accelerations, positive accelerations, negative velocities, positive velocities, and realizing that you do have to keep track of all these things. This equation, hopefully, you take your velocity or your speed, multiply it by the time it took, and that's where you ended up. But remember, for these constant acceleration problems, you can oftentimes use this V average, like I just said, you can use this V average to your advantage. If you know that you have constant acceleration, you can figure out your final position because that velocity is increasing all the time and it's not a particular velocity that you're traveling at through the entire trip. So, okay. Just hang on, we'll see I'm going to do some examples now and we'll see how to use these equations. Okay, here comes another car. Let's say that this car starts out, or cart, or whatever you want to call it, starts out, and at t equals 0, v is equal to 0. So that's v initial. Okay? It takes off, makes it down to here. Down here, it's V is equal to, we'll call it V final. V final is equal to 100 kilometers per hour. And the trip took 60 seconds. So that's a pretty slow car. Took a whole minute to get up to 100 kilometers per hour. That's not very fast. All right. So the question is, how far did it travel? Okay. Well, you can take that average velocity. I'm going to do it a couple of ways. You can take the average velocity and multiply it by the time. What's the average velocity? 50 kilometers per hour, right? From what I just did. Okay, I'm going to do it a couple of ways. I'm going to use that equation that has x final is equal to x initial plus and all of that stuff. and we'll calculate it using V average. Okay. All right, so I'm going to convert this to meters per second. 100 kilometers per hour multiplied by 1,000 meters per 1 kilometer multiplied by 1 hour is equal to 3,600 seconds. And let's see what I got. I got this equal to 27.8 meters per second. So V final is 27.8 meters per second. Okay? Well, I know from what I wrote down previously that the acceleration is equal to V final minus V initial divided by T or delta T. T initial is equal to 0, so we're just going to call it T. All right, so the acceleration is equal to 27.8 meters per second, that's V final, minus 0, just for completeness. V initial was equal to 0, and T was equal to 60 seconds. Okay, so the acceleration here, you guys still there?
Yes.
Thank you. The acceleration is equal to, if you do this calculation, the acceleration is equal to 0.463 meters per second squared. So if you were asked, okay, what's the acceleration? It's straightforward. You're plugging it into that equation that we already know, V final minus V initial divided by delta T. Now, we know the time, we know the acceleration, we know V initial. We're in a position to use that quadratic equation to solve for the final position, okay, or how far the cart traveled. Okay, so X, this is the one I'm going to use. X final is equal to X initial plus V initial T plus A over 2 T squared. Okay, well, X initial, I didn't put it up here, but I'm going to let X initial equal 0. So this is 0. V initial is equal to 0. That term's 0. So X final is equal to A over 2 T squared. All right, plug that in. We had the acceleration was 0.463 meters per second squared. Divide that by 2, and I don't have enough room, but I'll multiply it by 60 seconds squared. Okay. Units work out right in this. If you have the acceleration, that's in meters per second squared. We're multiplying by seconds squared, and we get something in meters. So it looks like the units work anyway. Okay. Do the calculation. Put it in your calculator. X final is equal to, this is what I got, 833.3 meters. Okay. So not quite a kilometer, 833 meters. That's one way you can solve this problem. How far did the cart travel? Another way is by looking at this, like I mentioned just a minute ago, and going, aha, this is constant acceleration. I know the final velocity. I know the initial velocity. Well, the average velocity is equal to V final plus V initial over 2. So this is equal to 100 kilometers per hour. That's an hour. Over 2. So this is equal to 50 kilometers per hour. That's the average velocity. And by knowing that, you have that x final is equal to x initial plus v average t. That was one of the equations that we wrote down a second ago. X initial is equal to 0. So this is equal to 50 kilometers per hour, which works out to be 13.89 13.89 meters per second multiplied by 60 seconds, and that is equal to 833.3 meters. Same answer that we had previously. Okay? What you're always doing in these problems, and students, especially when we get to projectile problems and problems in 2 dimensions, students always ask, how do I know which equation to use? How do I know what to use to, which equation do I use to solve the problem? You have to be very systematic on solving these. You guys, I didn't go over problem solving skills with you all, but oftentimes I do. You have to do those things that if you made it this far to get to Physics 1, you've got some good problem solving skills, hopefully. You got to draw a picture, label, write down the things you know, and then based on those variables that you look at the equation and find out, okay, I know x initial, v final, how long it took, okay? That leaves me one unknown in the equation that I had previously. It also leaves me one unknown here, okay? The way we're going to solve all these problems, and from Physics 1, from today forward, is draw a picture, label, write down the equations. I'm going to spend a minute thinking about the physics. So, anyway, that's my spiel on problem solving. Any questions on that?
I think so.
Okay, thank you for responding. All right. Let's work a little more complicated problem. And I'm going to post the homework for Chapter 2 sometime this afternoon. Look, I am very, I apologize for sending out that email so late last night. I mean, I got started on sort of editing what I did yesterday and trying to get it uploaded and all that, and it took YouTube forever to upload. Well, it wasn't so much YouTube. It took my Wi-Fi forever, and then YouTube took like an hour to process the video. So, I don't know. Anybody has any suggestions on that? I'm willing to listen. Get a faster internet. I got gig speed internet, but the upload speed is not good. So, okay. Here's a cute little problem. Once again, here's a cart. Let's say it's traveling at 35 kilometers per hour. Okay. This is a car. Here's a truck. Looks like Frankenstein's shoe. Okay. And it's traveling at 50 kilometers per hour in the opposite direction. This is, let's say x, yeah, I'll just call this x equals 0. And down here is x equals 500 meters. So half a kilometer. Let's say that the truck is slowing down. The truck is slowing at something reasonable, 0.15 meters per second squared. Okay. This car is just traveling at 35 kilometers per hour. The truck is traveling at 50 kilometers per hour in the negative direction. And it starts slowing down right here at 500 meters. It starts slowing down at a rate of 0.15 meters per second squared. Here's the question. Where do, that's a funny do they pass? Okay. So they're not going to collide. They're not going to collide. They're not on a head-on collision with one another. So they're gonna, there's 1D motion. So the question is, where do they pass? All right. Let's talk about the direction of these vectors, of these, the accelerations and the velocities and so forth. So for the car, all right, V initial, I guess I'll put V, let me make it some subscript so you can really get confused. Okay, so V car initial is equal to 35 kilometers per hour, all right? V car final is equal to 35 kilometers per hour. It's doing nothing. It's just traveling in the sense of it's not speeding up or slowing down. It's just traveling along happily at 35 kilometers per hour. All right. Acceleration for the car. Well, obviously, if it's no change in velocity, a car is equal to 0. X initial for the car. X car initial is equal to 0. Okay? Pretty simple for the car. Let's talk about the truck. For the truck, V sub T initial, so that's V truck initial, is what? I'll give you a moment to think about it. Well, it's obviously a magnitude of 50 kilometers per hour, but it's negative. Negative 50 kilometers per hour. Okay. Negative 50 kilometers per hour. All right. X truck initial. That's equal to 500 meters. Okay? What about the acceleration for the truck? Is the acceleration for the truck positive or negative?
Would it be negative since it's slow?
That's what you want to think. That's what you want to think in your mind, that it should have a negative acceleration because it's slowing down. But The truck is traveling in the negative direction. For it to be slowing, it better have a positive acceleration. You following me on that? Remember what I talked about yesterday? If those,
Look at the little chart yesterday.
yep, if those vectors, if the velocity is in the positive direction and the acceleration is in the negative direction, that's slowing. If the velocity is in the negative direction and the acceleration is in the positive direction, that's slowing down. Meaning if those directions are opposite, it's slowing. Those directions, velocity and acceleration, are in the same direction, whether they be positive or they be negative, it's speeding up. Okay, so the acceleration for the truck is equal to plus 0.15 meters per second squared. Okay, that's a plus, not a t. I put that there for emphasis, meaning the velocity is in this direction, that's the negative direction. The acceleration is positive. Okay. When I taught this class out of Resnick and Halliday, I know we're using Survey now, but there was a famous, I don't know, all the students knew about this problem that I called red car, green car. And red car, green car was this problem, but they didn't give you enough information. This one's going to be pretty straightforward once we sort of figure it out. So for red car, green car, you had to solve two equations and two unknowns, which is a little bit of a pain. So I'm not making you do that. And when I told students, I guess last year, that I was switching to Survey because of the university, wasn't my choice, it was the university's choice. They all threw a fit. They're not going to have to do red car, green car. It's going to, they need to suffer like we did. But anyway. So no red car, green car. You got this. For the car, not much going on. 35 kilometers per hour positive. For the truck, negative 50 kilometers per hour. That's V truck initial. X truck initial down here at 500 meters. And the acceleration of the truck is positive 0.15 meters per second squared. Okay. So the question is, where do they meet? So I'm going to, as always, I'm going to convert these numbers to meters per second and so forth. So I'll do that quickly. I'm not going to write out all the conversions. 35 kilometers per hour is equal to 9.72 meters per second. 50 kilometers per hour is equal to 13.9 meters per second. Okay. What else do we need? That's probably it. The acceleration is already in meters per second squared. So what we want to happen is, to answer the question, where do they meet? We want that X car final is equal to X truck final, right? That's going to be where they meet. Cars coming this way, trucks going this way, and we want to find out when these values are equal in that interval, okay? So X car final is easy. It's traveling at a constant speed, so 9.72 meters per second t. X initial for it, I already wrote that down previously. X car initial was equal to 0, remember? So X truck final is equal to, we're going to have to use that equation that is the big long one that's got t squared in it. Because the first thing we're going to have to do is we're going to have to find the time that they meet. Then we'll have to find, based on that time, how long it took them to meet. We can figure out the position. So X truck final is equal to 500 meters. That's X initial. Minus 13.9 meters per second T. I have to keep that negative in there. V initial is negative. Plus 0.15 meters per second squared, that's A, over 2 times T squared. So there's the equation for the car. There's the equation for the truck. Set those equal to one another. Solve. I'll do that now. So we have 9.72 meters per second T is equal to 500 meters. I know I'm going to run out of room, but that's okay. Minus 13.9 meters per second T plus 0.15 over 2, you get 0.075. I'm just dividing this number by 2, T squared. Okay? That's a 5. How do you solve an equation like this? Well, plug it into your calculator. I mean, you know, standard stuff. Collect variables first and then plug it into your calculator. I'll do that. I actually use the quadratic formula because that's how I learned. Let's see, 0. I know how to plug it in the calculator, maybe. But, wait, yeah. T squared minus 23.61 meters per second T plus 500 meters. Let me get rid of this. Plus 500 meters is equal to 0. Now it's in standard quadratic form. A x squared plus b x plus c. And you all know how to solve that. So writing it out, let's see, I get t from the quadratic formula, negative b. So I get 23.61 plus or minus the square root of b squared. I'm suppressing the units here, so I'm solving for the numerical value. Minus 4ac. A is 0.075. C is 500. All of that over 2 times A. So that's 2 times 0.075. And I get T is equal to 22.83 seconds. That's one answer. And if it's quadratic, if it's a polynomial of order 2, you always get 2 answers. The other answer is 292 seconds. Anybody got an inkling on which time we should choose? Or what do the times have to do with the physics, I guess I'm asking. This one is where they meet the first time. What does this one represent? This represents a silly answer based on the truck. Okay, these dynamic equations, they're running out into time, okay? And this represents kind of a silly situation where they pass, okay, here comes the car. Here's the truck slowing down, they pass. They pass at 22.83 seconds. The car just keeps going, but what happens to the truck? The truck slows down to a stop and then starts accelerating in the other direction, right? The acceleration was positive, so the truck's going to slow down and start going in the other direction. And eventually the truck, in reverse, is going to speed up and catch the car, and they're going to pass again. And then the truck, okay. It's kind of silly for the way we set up the problem, but there are some situations like this, like an object going out with a rubber band and coming back and passing some object, passing twice, okay? But this is the time at which they meet on that path between them, all right? The silliness of the truck slowing down, coming to a stop, going in reverse at this accelerator, 0.15 acceleration, all right, it's 292 seconds. So that takes a while, about 5 minutes, right? Okay, so let's go ahead and calculate where, because the statement that I made was where do they meet? So you can use either equation to figure out where they meet. X car final is equal to X car initial, which is 0, plus the velocity of the car, which was 9.72 meters per second, multiplied by 22.83 seconds. And that is equal to 222 meters. Okay? So that's X car final. That's also X truck final, right? So they don't meet right at the halfway point. They meet, the truck actually sort of catches up with the car before the car can pass the halfway point. All right? And just if you're curious, using this time, X car final is way down at, this is for the second time, 9.72 meters per second, multiplied by 292 seconds, and this is equal to 2,838.7 meters. So almost 3 kilometers down the road from where the car started. Okay. In the silly situation. Have you any questions on that?
I don't think so.
Okay, thank you. So I'll go ahead and post some homework for chapter 2. We haven't gotten to all of it yet by any means, but you can give the, a few of the problems a try, and certainly if you have questions, you can email me, or you can wait till class tomorrow and ask me questions. We can go over the problem. Generally, I'll go over all the problems at some point anyway. I'll probably make a separate video going over all the problems. So, okay. I think this is a pretty good place to stop today. Has anyone got any questions?
When will the homework for chapter 2 be due?
The end of the term.
So we have the whole entire, like, summer course to do it?
Yep.
Thank you.
I recommend that you don't wait till the end, but I don't do that during the normal semester. I typically cut the homework off on test day, but due to the circumstances that we have, I mean, I could foresee you getting sort of, stuck on problems and not being able to get those done. So, it's up to you. It's like I said, if you want to learn the material and do the work, that's up to you. If you want to check everything and, Google everything, okay. But learning this material will serve you quite well in the future. And it's fun, I think. It is for me anyway.
Problems for, like, the acceleration, kind of like the examples we just did?
Yeah, sure. Did you say in the homework will there be problems like this?
Yeah.
Oh, absolutely, yeah. I mean, go ahead.
Are you going to get the homework off the book, or are you going to make like questions yourself?
The homework will be out of the WebAssign problems. I may write a few problems, but, and also if I guess maybe you're leading up to like the test problems, what they're going to be like. If you look on my webpage, there are previous tests. There's a test bank, and you can look at how I write the problems. Yeah, the homework, the online homework will be from WebAssign. It'll be from Survey. That's why we have it. It's part of why we have it. I mean, it's not just there for us to, it's not just a reference text. It's actually text that we're using, and you should be reading it. You should be working problems from it, and so forth. Go ahead.
Could you give us your webpage?
The webpage is on the syllabus. If you Google TCLARKE2, I think I'm the first hit. So just Google TCLARKE2, and it'll come up Dr. Clark's webpage. And then you scroll down to Physics 150, and everything is there. Should be. Any more questions?
Doesn't look like it.
What's that?
I said I don't think there is.
Okay.